Welcome to Lecture 3B, a mathematical toolkit lecture. Lecture 3 gave us the geometry of flow matching, straight lines from noise to data, probability paths, conditional velocities. Lecture 4 will build the training algorithm, which uses expectations, losses, and gradients heavily. This lecture bridges that gap. We will build every concept Lecture 4 needs, with code examples so you can see exactly what the math looks like in practice. By the end, Lecture 4's formulas will feel natural rather than intimidating. Here is where we sit in the lecture series. Lectures 1 through 3 built up the geometric picture of flow matching. Velocity fields push distributions, conditional paths connect individual noise points to data points. Linear interpolation gives us the simplest path. Lecture 4 will derive the training algorithm, the conditional flow matching loss. But that derivation uses expectations over multiple random variables. Conditional expectations, properties of the MSE gradient, and Monte Carlo sampling. If these concepts are not fresh in your mind, Lecture 4's formulas will feel like a wall of notation. So this lecture builds each tool one at a time. For every concept, we will see the math, the intuition, and a concrete PyTorch code example. Let us begin. Let us start with the most basic operation, sampling. When we write x0 tilde p, we mean draw a random sample from the distribution p. For flow matching, p is usually a standard Gaussian, n of 0, I. That just means generate a random point where each coordinate is drawn independently from a bell curve centered at 0. When we write x1 tilde q, we mean pick a random point from the data distribution. In practice, this means randomly selecting a data point from our training set. For our running example, q is the 2 moons dataset from scikit-learn. The key point: each sample is independent. Every time you sample x0, you get a fresh random point. Every time you sample x1, you get a different data point. This independence is what makes the math work. Here is the code. 2 lines do all the work. Torch.rand of 256, 2 generates 256 two-dimensional points from a standard Gaussian. Each row is one noise sample. Make_moons generates 256 points from the 2 moons dataset, our target distribution. Notice the shapes are identical, 256 by 2. This is important because in flow matching, we will pair each noise point with a data point, 1 to 1. The noise mean is approximately 0, and the standard deviation is approximately 1, exactly as expected from n of 0, I. These 2 lines are literally the first 2 lines of every flow matching training step. Everything else builds on this. Now we connect noise to data with linear interpolation. The formula is simple. xt equals 1 minus t times x0 plus t times x1. This is just a weighted average. At time 0, the weight is entirely on x0, the noise point. At time 1, the weight is entirely on x1, the data point. At time 0.5, you are exactly halfway between them. The velocity, the derivative with respect to t, is x1 minus x0. Notice this is constant. It does not depend on t at all. The particle moves in a straight line at constant speed from noise to data. This constant velocity is exactly what we will ask the network to predict in Lecture 4. This is the linear conditional path from Lecture 3. What is new here is that we are thinking of it computationally. Given tensors x0 and x1, computing xt is just one line of arithmetic. There is a subtlety in the formula xt equals 1 minus t times x0 plus t times x1 that is worth pausing on. For a fixed value of t, xt is a random variable. Why? Because x0 and x1 are random. Every time you draw a new noise point and a new data point, you get a different xt. On the left, we see 3 specific sample pairs. Each pair gives one straight line. Given a specific x0 and x1, the path xt is completely deterministic. There is no randomness left. At t equals 0.5, each pair gives a specific point on its line. On the right, we see what happens with many pairs at once. At t equals 0, the collection of all x0 values forms a cloud distributed as p, the source distribution. At t equals 1, the collection of all x1 values forms a cloud distributed as q, the target distribution. At t equals 0.5, you get an intermediate cloud, a distribution we call p at time 0.5. This is the probability path from Lecture 3, now seen from a computational perspective. The distribution of xt changes smoothly from p to q as t goes from 0 to 1. The shape of this intermediate distribution depends entirely on what p and q are. If p is a Gaussian, the cloud at t equals 0 is a Gaussian blob. If p were a log normal instead, the cloud at t equals 0 would be skewed, and the intermediate distributions would look completely different. Let us see this with actual numbers in code. Here it is in code. We have the same target distribution, 2 moons, but 2 different source distributions. The first is a standard Gaussian, which is the standard choice in flow matching. The second is a log normal, where we exponentiate Gaussian samples to get positive, skewed values. The interpolation formula is identical in both cases. 1 minus t times x0 plus t times x1, but because x0 is drawn from a different distribution, the intermediate point, xt at time 0.5, lives in a completely different part of space. Look at the print statement at the bottom. For one specific pair, x0 is minus 0.31, 1.22. x1 is 0.98, 0.45. And xt at time 0.5 is 0.34, 0.84. That is just the midpoint. One concrete 2D point. No mystery. The key takeaway: xt is a random variable because its inputs are random. But for any specific draw of x0 and x1, xt is just a deterministic weighted average, a concrete pair of numbers. The choice of source distribution p affects what the intermediate distributions look like, but the interpolation formula is always the same. In standard flow matching, we always use a Gaussian source because it is easy to sample from and has nice mathematical properties. But the framework works for any source distribution. Here's the interpolation in code. One line computes xt 1 minus t times x0 plus t times x1. The velocity is even simpler, x1 minus x0. The visualization shows the distribution at 5 time steps. At t equals 0, you see the Gaussian noise cloud. At t equals 0.25, it starts to deform. By t equals 0.5, you can see hints of the 2 moons. At t equals 0.75, the moons are clearly forming. At t equals 1, you have the clean 2 moons dataset. This is the probability path from Lecture 3, but now you can see it as actual code, 2 lines of tensor arithmetic. Every point takes a straight line path from its noise position to its data position. Expectation is the single most important concept for understanding flow matching's training algorithm. When we write e of f of x, we mean what is the average value of f of x if we could evaluate it over all possible x. Let us build this in 3 steps. Step 1. We have a probability distribution p of x. In this picture, it is a Gaussian. This tells us which values of x are likely and which are rare. Step 2. We have a deterministic function f. There is nothing random about f itself. Given any specific x, f of x is a definite number. The randomness comes entirely from x, which is drawn from p. We sample several x values and evaluate f at each one. The orange dots show f of xi for 5 samples. Step 3 we're jangling? We average those values. The result is a single number, e of f of x. Not a function, not a distribution, one scalar. The randomness in x has been averaged out. In practice, we compute this with Monte Carlo sampling. Draw n samples from p, evaluate f at each, and take the mean. This estimator is unbiased. Its expected value equals the true expectation for any sample size n. Like, larger n just reduces the variance of the estimate. This is exactly what torch.mean does. One important note before we move on. E of f of x is a scalar, a single number. But the conditional expectation e of y given x equals x, which we will see next, is a function of x. For each value of x, you get a different number. That distinction will be critical in Lecture 4, where the marginal velocity is a conditional expectation, a function defined at every point in space. Let us see expectations in code. Torch.mean is the expectation operator. First, E of x for a standard Gaussian. We draw 10,000 samples and take the mean. The result is approximately 0, as expected. E of x squared should equal the variance, which is 1 for a standard Gaussian, and it does. E of the squared norm for a 2D Gaussian should be 2, 1 per dimension. Check. The bottom loop shows convergence. With 10 samples, the estimate bounces around. With 100, it is tighter. With 10,000, it is very close to 0. This is the law of large numbers in action. Here is the connection to training. Every time PyTorch computes a mini-batch loss and calls backward, it is estimating an expected gradient via Monte Carlo. The mini-batch size is your in. Larger batches give smoother gradients, just like more samples give better expectation estimates. Conditional expectation is the most important concept in this lecture. It is what connects the easy conditional velocities from Lecture 3 to the hard marginal velocity that Lecture 4 needs to approximate. E of y given x equals x means the best prediction of y, knowing x. Imagine you have a cloud of x-y pairs. For a specific value of x, the conditional expectation is the average of all the y values at that x. If you think of x as position and y as velocity, then E of y given x equals x is the average velocity at position x. Crucially, the conditional expectation is the function that minimizes the expected squared error. No other function of x can do better at predicting y, on average. This optimality property is what makes it central to flow matching. Here's the direct connection. In flow matching, the marginal velocity at position x is ut of x equals E of x 1 minus x0 given xt equals x. That is a conditional expectation. It says, given that a particle is at position x at time t, what is the average direction it should move? This averages over all possible data points that could have produced this position. Let us compute a conditional expectation in code. We generate data where y equals 2x plus Gaussian noise. The true conditional expectation E of y given x equals x is exactly 2x. The function cond_xp estimates this using kernel-weighted averaging. For a query point x, it gives higher weight to nearby samples and lower weight to distant ones, then computes the weighted average of y. This is a non-parametric estimate of the conditional expectation. The results confirm it works. At x equals 1, the estimate is approximately 2. At x equals minus 2, the estimate is approximately minus 4. Each is close to the true value of 2 times x. In flow matching, the network ut theta of x is learning exactly this kind of function. Given a position x at time t, predict the average velocity. The network is a parametric approximation to a conditional expectation trained by minimizing MSE, which brings us to the next concept. Now we come to the MSE loss, mean squared error. This is the loss function that flow matching uses, and it has a property that is absolutely critical. The loss is simple, the squared distance between what the network predicts and the target. The gradient with respect to the prediction is 2 times the prediction minus the target. This points from the prediction toward the target with magnitude proportional to the error. Standard stuff. But notice something specific about this gradient. It depends linearly on the target. If you double the target, the gradient changes by a proportional amount. If you replace the target with an average of targets, the gradient is the average of the individual gradients. This linearity might seem like a minor mathematical curiosity. It is not. It is the single property that makes flow matching training possible. Let me show you why on the next slide. This is the most important slide in this entire lecture. It is the mathematical reason flow matching works. Here's the property. If your target is an average, E of y, then the gradient of the MSE loss with that average target is exactly equal to the expected gradient with individual targets. Written out, nabla of the norm of pred minus E of y squared equals E of nabla of the norm of pred minus y squared. Why does this matter? Think about it in terms of 2 training strategies. Method 1, compute the average target E of y, then take one gradient step. This requires knowing all possible targets and averaging them, which is intractable. Method 2, sample individual targets y, I, one at a time, compute the gradient for each, and average the gradients. This only requires one sample per step. The key property says these two methods produce exactly the same gradient, not approximately, exactly. Now connect this to flow matching. The average target E of y is the marginal velocity ut of x, which requires integrating over the entire dataset. That is intractable. But the individual targets yi are just x1 minus x0, the conditional velocity for one noise data pair. That is trivially easy to compute. The gradient linearity of MSE guarantees that training with these easy individual targets gives the same gradients as the intractable average. This is the conditional flow matching loss, and this is why it works. Let us verify this in code. We have a prediction vector and 3 possible targets. The average target is their mean. Method 1. Compute the MSE loss between the prediction and the average target, then call backward. This gives gradient 1. Method 2 for each individual target. Compute the MSE loss and gradient separately. Then average the 3 gradients. This gives gradient 2. The result would be both methods give tensor -2, -1. They are identical. Not close, not approximately equal. Exactly the same, to machine precision. This is not a coincidence. It is a direct consequence of the gradient 2 times pred minus target being linear in the target. When you replace the target with an average, the gradient automatically becomes the average of the individual gradients. In flow matching, this means you never need to compute the intractable average velocity. Just sample one data point, compute the easy conditional velocity, and take a gradient step. Over many steps, the gradient averages converge to what you would have gotten with the intractable marginal. Now let us put all 5 concepts together into a single flow matching training step. Step 1, sampling. Draw a noise point x0 from the Gaussian and a data point x1 from the dataset. We covered this in slides 3 and 4. Step 2, interpolation. Pick a random time t and compute xt, the interpolated position along the straight line path. Slide 5. Step 3, the target velocity. For the linear path, this is simply x1 minus x0, the direction from noise to data, also from slide 5. Step 4, the MSE loss. Feed xt and t into the network, get the predicted velocity, and compute the squared error against the target. Slide 11. Step 5, backpropagate. Compute the gradient and update the network weights. The gradient linearity from slide 12 guarantees that this single sample gradient points in the right direction on average. That is it, 5 steps, each one a concept we built in this lecture. In lecture 4, this will be written as one formula, the conditional flow matching loss. But now you know what every piece means and why it works. Let us recap what we built in this lecture. 5 mathematical tools, each simple on its own, but together they form the complete foundation for the flow matching training algorithm. Sampling from distributions, how to draw noise and data points in PyTorch. Linear interpolation, how to walk from noise to data in a straight line and how the velocity is constant. Expectation, the average over randomness, computed in practice via torch.randn. Conditional expectation, the best prediction given partial information, which is exactly what the velocity network learns. And most importantly, the gradient linearity of MSE, the algebraic identity that lets us replace an intractable average target with easy individual targets. In Lecture 4, you will see the conditional flow matching loss for the first time. It will contain expectations over multiple random variables, conditional velocities, and a claim that 2 different losses produce the same gradients. Thanks to this lecture, you now know exactly what each piece means and why the gradient equivalence holds. The formula will not be a wall of notation. It will be a precise statement of the 5 steps we just built. See you in Lecture 4.